We physicists have waited patiently for a considerable length of time since 1916. For this moment, this is a close-up of a black hole, one of the most enchanting and confounding phenomena in the universe. Black holes are immense in terms of gravity, yet in many ways they are almost intangible to us. A black hole, weighing perhaps 2 to 4 million times the mass of the Sun, remains a subject of fascination over the past 20 to 30 years. We have gone from knowing virtually nothing about black holes to gradually uncovering more, and now things have taken an even more extraordinary turn. Recently, Michio Kaku reported that we have finally caught a glimpse of what lies inside a black hole. This new data sheds light on the subtleties that the scientific world might have initially overlooked. Join us as we dive deeper into black holes and uncover what is inside them. Space is vast and terrifying, but what are black holes? Before we delve into the subtleties of Michio Kaku's findings, we need to cover the basics. While most of us have a general idea of what black holes are, there are still gaps in our understanding. In 1916, Albert Einstein published his theory of general relativity, which predicted the existence of black holes. At that time, black holes were purely theoretical. It took another 50 years for established scientists to find evidence proving their existence. This breakthrough occurred in the 1960s, when scientists studying the star signal X1 observed a remarkably bright blue star emitting X-rays. The star was not a dead object, but was orbiting a massive, dark entity. Further examination revealed that the X-rays were not simply drifting aimlessly, they were being drawn into the dark entity. They orbited this mysterious object was named a black hole. This discovery was monumental because it proved that black holes were not just the product of Einstein's vivid imagination, they were real. But while this was exciting, it also meant there was an enigmatic entity in space that we desperately needed to learn more about. Scientists worldwide began studying Cygnus X1, located in the constellation Cygnus, approximately 6,000 light-years from Earth. This black hole is no small revelation. It is more than 10 times brighter than the Sun and is, of course, incredibly dense, giving it a powerful gravitational pull. The concept of a black hole is both fascinating and frightening. It is a region in space where gravity is so strong that nothing, not even light, can escape. Anything that comes too close to a black hole will be pulled in and lost forever. The discovery of Cygnus X1 marked the beginning of an era of black hole research. Since then, scientists have searched for other black holes and discovered that there may be as many as 100 million black holes in the Milky Way alone. However, due to their extraordinary difficulty to detect, the exact number remains uncertain. Despite this, we now know that there are likely millions of black holes in the Milky Way, which only makes studying them more crucial. What makes black holes so unique? The key feature of black holes is their gravity. Their gravitational pull is so intense that anything entering them is compressed to an extreme degree, forming what is known as a singularity. In simpler terms, black holes are like enormous vacuum cleaners pulling in everything around them. One of the scariest aspects of studying black holes is the fact that if someone were to fall into one, they would eventually reach a point where they are stretched into a single line. This process, called spaghettification, happens gradually, and the person would die long before the actual collapse of space-time occurs. Fortunately, the nearest black hole to Earth is about 500 light-years away, so there's no immediate danger. In 2021, researchers produced the first clear photo of a black hole, the M87 black hole. This black hole was captured over several nights, and with each image, scientists gathered more evidence. They had to combine the individual photos to fill in the gaps which allowed them to confirm that black holes have three distinct layers contrary to popular belief. A black hole is not just a single void of nothingness. To even reach the nothingness of a black hole, one must first pass through its first two layers. The first layer is called the event horizon. This is the point of no return. Once you cross it, there's no escaping the black hole's gravitational pull. The second layer is the photon sphere, where light orbits the black hole. Any light entering this region is trapped and cannot escape due to the immense gravitational force. Finally, we come to the third layer, the singularity. This is the core of the black hole, where everything that enters is compressed into an infinitely small point. At the singularity, the laws of physics as we know them break down entirely, and we cannot predict what happens next. Each black hole is as unique. While they may follow the same basic three-layer structure, their behavior and characteristics can vary greatly. How do scientists study black holes? Studying black holes presents significant challenges, since anything entering the event horizon is pulled into the singularity. It is impossible to send a probe to investigate directly. For this reason, scientists must study black holes indirectly by observing the radiation they emit and the gas and dust surrounding them. Despite these challenges, scientists have developed many theories about the formation of black holes. One of the most compelling is that black holes are formed from the collapse of massive stars. When a star exhausts its fuel, it can no longer produce enough energy to counteract gravity. The star then begins to collapse in on itself, becoming denser and denser. If the star is massive enough, this process continues until it forms a singularity. In an attempt to understand black holes better, NASA turned its attention entirely to the center of the M87 galaxy. Astronomers observed a massive whirlpool of incredibly hot hydrogen gas spinning at a staggering speed of 1.2 million miles per hour. This rotation should have caused the gas disk to fly apart, but it didn't. Scientists concluded that an enormous mass at the galaxy center was holding it together, a mass equivalent to 2 to 3 billion suns. The discovery of this massive black hole in M87 confirmed the existence of massive black holes at the centers of galaxies, but even this understanding only scratches the surface. Alternative theories and mysteries. While the theory that black holes form from collapsing stars is widely accepted, there are alternative theories regarding their origin and nature. Some scientists suggest that black holes may have formed shortly after the Big Bang, during the early stages of the universe. These hypothetical black holes, known as primordial black holes, could vary in size and mass from microscopic to super massive. Another fascinating theory proposes that black holes might act as gateways to other universes. This idea stems from the concept of a wormhole, which is a hypothetical tunnel in space-time that connects two separate points. While there is no direct evidence for wormholes, they remain a popular subject in theoretical physics and science fiction. Additionally, there is ongoing debate about what happens inside the singularity of a black hole, since the laws of physics as we know them break down at this point. Some scientists believe it might hold the key to a unified theory of quantum gravity and understanding that bridges the gap between general relativity and quantum mechanics. What's next for black hole research? The first photo of the M87 black hole was a groundbreaking achievement, but it was only the beginning. Scientists are now working to capture clearer and more detailed images of black holes using advanced telescopes, such as the Event Horizon Telescope. EHD, in addition to imaging, researchers are studying gravitational waves, ripples in space-time caused by the collision of massive objects like black holes. The detection of gravitational Waves by LIGO Laser Interferometer. Gravitational Wave Observatory has opened up a new way of studying black holes, providing insights into their formation and behavior. One of the most exciting developments in black hole research is the study of their role in galaxy formation and evolution. Massive black holes like the one in M87 are believed to influence the growth and structure of their host galaxies. Understanding this relationship could reveal new information about the history of the universe, a look into the unknown. Despite decades of research, black holes remain one of the greatest mysteries of the cosmos. They challenge our understanding of physics, push the boundaries of technology, and inspire countless questions about the nature of reality. What lies beyond the singularity? Are black holes connected to other universes? Could they hold the answers to the origins of the universe itself? For now, these questions remain unanswered, but with every new discovery, we come one step closer to unlocking the secrets of these enigmatic cosmic phenomena. The journey to understand black holes is far from over, and the next breakthrough could redefine our understanding of the universe as we know it. In 1963, New Zealand mathematician Roy Kerr utilized Einstein's conditions of gravity to give the best portrayal of a rotating black hole. He showed that a turning black hole wouldn't collapse into a point as previously thought, but rather would form a ring of fire or a thin disk. The disk would spin so rapidly that outward forces would prevent it from collapsing. This rotating disk of matter is known as the aerosphere, and it's the region surrounding the black hole where the laws of physics begin to break down. However, the most intriguing feature of core model was that it predicted the existence of an Einstein-Rosen bridge, otherwise known as a wormhole. This is a hypothetical entry through space-time that connects two separate regions of the universe, or even two parallel universes. The idea is that if someone were to fall into a black hole, instead of being crushed to nothingness, they would be pulled through a passage in the ring of fire and ejected through a white hole into a parallel universe. To understand how this works, we need to examine the concept of space-time in Einstein's theory. According to his hypothesis, the reality we experience isn't made of discrete elements, but is interconnected, forming a four-dimensional fabric known as space-time. Objects with mass warp this fabric, creating a gravitational field that causes other objects to be drawn toward them. Now imagine a sheet of paper representing space-time. If you mark 2 points on the paper and draw a line between them, this represents how objects travel through space-time. But what if you could fold the paper in half and create a shortcut between the 2 points? This is a fundamental idea behind a wormhole, a shortcut through space-time that connects two distant points. Instantly, wormholes aren't just a science fiction concept, they are in fact a prediction of general relativity. However, no one has ever observed one directly. The reason is that wormholes are inherently unstable and would collapse quickly. Nevertheless, the existence of an Einstein-Rosen bridge would imply that black holes are not only massive vacuum cleaners, but could also serve as gateways to different regions of space-time. So could we use a wormhole to travel through existence? Unfortunately, the answer is probably no. Not yet. Even if we could stabilize a wormhole, it is unlikely we could use it to travel faster than light. Einstein's theory of special relativity predicts that the speed of light is a hard limit on how fast anything can move through space-time. Despite this, the theory of wormholes and black holes as pathways to different parts of the universe, or even to different times, has been a subject of fascination and speculation among physicists for decades. The possibility that there might be shortcuts through the fabric of space-time allowing travel across vast distances or even into the past could be revolutionary if we could achieve it. One of the most captivating ideas in this field of study is the Kerr wormhole, named after the mathematician Roy Kerr, who first described Einstein's conditions of gravity. This type of wormhole is essentially a theoretical tunnel through space-time that could connect two distant points, such as two different universes or even two separate times within the same universe. The Kerr wormhole is ring-shaped like the mirror in Alice in Wonderland and could theoretically transport a traveler to another universe or era where the laws of physics might be entirely different. However, what may seem extraordinary at the destination could be entirely normal there. While the possibility of wormholes for interstellar or time travel is exciting, it remains a topic of debate among physicists. Some argue that wormholes, and particularly black holes, might be unstable or impossible to traverse due to the extreme radiation and subatomic forces surrounding their entrances. Critics point out that Einstein's conditions of gravity, which describe wormholes and black holes, work only for gravity, not for the quantum forces that govern radiation and subatomic particles. To truly understand the nature of these phenomena, a new theory is needed, one that can unify the laws of gravity with a quantum theory of radiation throughout the universe. This is known as a theory of everything, a single framework that can combine Einstein's theory of gravity with quantum theory. Michio Kaku, a renowned theoretical physicist, has been working on a theory of everything for decades. One promising candidate is string theory. String theory combines gravity with the theory of radiation. It suggests that subatomic particles are actually tiny, vibrating strings, and that the universe is a symphony of these strings, just as different musical notes correspond to different vibrations of a violin string. Different particles in nature correspond to different vibrations of a string. A fascinating aspect of string theory is that as the string moves through time, it bends the fabric of space around it, creating black holes, wormholes, and other unique solutions to Einstein's equations. This means that string theory not only unifies Einstein's theory of gravity with quantum theory, but also explains many of the strange phenomena observed in the universe. However, there's a catch. The extra dimensions of space-time required by string theory are so small that we cannot directly detect them